Example 6, finding the zeros of a polynomial function with complex zeros. We want to find the zeros of f of x, which is equal to 3x cubed plus 9x squared plus x plus 3. Step number 1, the rational zero theorem tells us that if p over q is a zero of f of x, then p is a factor of 3 and q is a factor of 3. P over q is equal to the factor of the constant term 3 over the factor of a leading coefficient 3. So the factors of 3 is plus or minus 1 and plus or minus 3, same thing in our denominator. So we end up with plus or minus 1, plus or minus 3, and plus or minus 1/3. So that means we're going to have a total of 6 possible rational zeros. So the first one that we try using synthetic division is when we get -1. So we put -1 and then we use the coefficients of each of those terms. So we have 3, 9, 1, and 3. Bring down 3, -1 times 3 is -3. 9 minus 3 gives you 6. -1 times 6 is -6. -6 plus 1 is -5. -1 times -5 is +5. And 3 plus 5 gives you 8. So we get a remainder that's 8. So therefore we cannot say that -1 is a 0. Now we're going to try 1. So we try 1. Bring down to 3. 1 times 3 is +3. 9 plus 3 is 12. 1 times 12 is 12. 12 plus 1 gives you 13. And then 1 times 13 is 13. And 13 plus 3 gives you 16. So we get a remainder. So 1 is not a 0. Next we have -3. So -3 we're going to bring down to 3. -3 times +3 is -9. 9 minus 9 is 0. -3 times 0 is 0. 1 plus 0 is 1. And -3 times 1 is -3. So 3 minus 3 gives you 0. So therefore we know that since we get a remainder of 0, then we can say that -3 gives us x plus 3, and that gives us a remainder of 0. So now we know that x plus 3 is a factor of this polynomial. So -3 is a 0 of that function. Now let's take a look at the quotient here. We have an x squared term, we have a 0 for the next term, and then 1. So this becomes 3x squared plus 0x plus 1, which becomes 3x squared plus 1. So the way we can write the polynomial right now is x plus 3 times 3x squared plus 1. So now we need to determine what the zeros of the function are. Well, we know that x plus 3 equals 0 gives us a 0 of x equals -3. And then we're going to set 3x squared plus 1 equal to 0. And then solve for x. So we subtract 1 to both sides. And then divide by 3. So we get x squared is equal to -1/3. And then if we take the square root of both sides, then we get x, which is equal to plus or minus I, because it's negative, times the square root of 1 over the square root of 3. And now if we rationalize the denominator, then we end up with x is equal to plus or minus I times the square root of 3 over 3. So what can we say? We can say that the zeros of the function are -3 and plus or minus I times the square root of 3 over 3. Now if we look at the graph of the function in figure 2, we can notice that x equals -3 on the graph crosses the x-axis, indicating an odd multiplicity of 1 for the 0 of x equals -3. Now also note the presence of the 2 turning points. This means that since there is a third degree polynomial, we are looking at the maximum number of turning points. So the end behavior of increasing without bound to the right and decreasing without bound to the left will continue. Thus, all the x-intercepts for the function are shown. So either the multiplicity of x equals -3 is 1, and there are 2 complex solutions, which is what we found for the multiplicity at x equals -3 is 3. Either way, our result is correct. So that means we have one x-intercept, but we have 2 imaginary solutions, and it doesn't cross the x-axis, which tells you that we have our turning points.